I'm going to talk about simulation in this lecture. Simulation is a very important topic for statistics and for a number of other applications. So I just want to introduce some of the functions in R that can be useful for doing simulation. So there are a couple of functions that are available for simulating numbers or variables from given probability distributions, probably the most important of which is the normal distribution. And so we can generate variates from the normal distribution by specifying a mean and a standard deviation for that distribution, and then calling the rnorm function. So the rnorm function will simulate normal random variables from a distribution that has a given mean and standard deviation. There are corresponding functions for the normal distribution that can be used to evaluate the probability density, to evaluate the cumulative distribution function, and also for evaluating the quantile function. So another function for generating random variables is the rpois function, which generates Poisson random variables from a Poisson distribution with a given rate. So there are a number of functions for generating random variables from kind of the standard probability distributions, and you can use these to run simulations. So probability distribution functions, there are basically four functions associated with them. And so for any given distribution like the normal distribution, there will be a function that starts with a d, a function that starts with an r, with a p, and a q. So there'll be four different functions for each distribution. So I've already mentioned that there's the rnorm function. So the rnorm function is for random number generation. There's a dnorm function which evaluates the density of the probability distribution for a given mean and standard deviation. There's the pnorm function, which evaluates the cumulative distribution, and there's the qnorm function, which evaluates the quantile function. So every distribution has these four types of functions. So for the gamma distribution, there will be a d gamma, an r gamma, p gamma, and a q gamma function. And for the Poisson distribution, there's the r pois, d pois, p pois, and q pois functions. So working with the normal distribution requires these four functions. So I mentioned there's dnorm, pnorm, qnorm, and rnorm, and you can see they each take a number of different parameters. All of the functions require that you specify the mean and the standard deviation because that's what specifies the actual probability distribution. If you do not specify them, then the default values are a standard normal distribution which has mean 0 and standard deviation 1. For the dnorm function, you can evaluate the density, and there's an option that allows you to evaluate the log of the density. Most of the time, when you evaluate the density function for a normal distribution, you're going to want to use the log of that value, but the default is false. For the pnorm function and the qnorm function, there's also an option to evaluate it on a log scale, but another option is whether or not you want to evaluate the lower tail of the distribution. So the lower tail, which is the default, is if you look at the probability distribution, it's the part that goes to the left. It's the lower tail. If you want to evaluate the upper tail, sometimes you want to do this. Then you want to say lower tail equals false, and that will evaluate the upper tail of the distribution. And finally, for rnorm, there's only two parameters, mean and standard deviation, and then n, which is the number of random variables that you want to generate. So if n is 100, you'll get a vector of 100 numbers that are drawn from the normal distribution. So just to be more explicit, if phi is the cumulative distribution function for the standard normal distribution, then pnorm is equivalent to phi, and qnorm is equivalent to the inverse of phi. So just quickly, if you want to generate some random variates, you can just call rnorm and pass it an integer, which is the number of variables you want to generate. So here I'm passing 10. And you can see that the vector that's produced will be random normal numbers which have mean 0 and standard deviation 1. If I wanted to generate a vector that had mean 20 and standard deviation 2, I just need to specify that explicitly in my call to rnorm. So here, this vector has are 10 random normal random variables, and their mean is roughly 20, and their standard deviation is 2. So anytime you simulate random numbers from any distribution for any purpose, it's very important that you set the random number generator seed, and this can be done with the set.seed function. So what's important to know is that on computers, when you generate random numbers, the numbers are not actually random, but they appear random, and that's the important thing. And so the idea is that if you wanted to generate the same set of random numbers again, you could if you wanted to, because the numbers are not actually random. They're what are called pseudo-random numbers. And so here I'm setting the seed to be 1. So the seed can be any integer you want. You just pass it an integer, and that's the seed. So here I'm going to set seed equal to 1, and then I'm going to generate 5 random normal random variables. And so here I've got my 5 normal random variables. They have mean 0 and standard deviation 1. If I generate another 5, you'll see that the vector is totally different because it's another random sample of 5. However, if I reset the seed to be 1 and I draw 5 again, you'll see that they're exactly the same as the first 5 that I drew. So when you set the seed, it kind of sets the sequence of random variables that's going to occur. And if you reset the seed, you kind of set the sequence to go back to where you started, and then it will continue to kind of generate random variables from there. So this is important because it allows for you to reproduce the random numbers that you generate. Now that might sound strange, because why would you want to generate the same random numbers twice? But in many applications, you do want to generate the same random numbers twice so that people can reproduce what you've done. And in particular, if there are some errors or problems in what you've done, you want to be able to get to kind of go back to the exact situation that produced those problems. So whenever you do a simulation, you always want to set the random number seed so that you can go back and get the same results. So I've demonstrated how to generate normal random variables, but of course you can generate random variables from other probability distributions. So the Poisson distribution is of course very popular. Here I'm generating a 10 Poisson random variables with a rate of 1. So of course Poisson data are going to be integer. Here I'm generating 10 Poisson random variables with the rate of 2, so you can see they're slightly larger. And then here I'm generating 10 random variables, Poisson random variables with a rate of 20. So for the Poisson distribution, the mean is going to be equal to the rate. So you can see that roughly in each of these 3 cases, the mean is roughly equal to the rate that I specified. I could also evaluate the cumulative distribution function for the Poisson distribution. So here in this first example, I want to know what is the probability that a Poisson random variable is less than or equal to 2 if the rate is 2. And so this is the probability, it's 0.67 roughly. If I want to know what's the probability that a Poisson random variable with rate 2 is less than or equal to 4, you can see the probability is getting bigger. And here I can see the probability that a Poisson random variable is less than or equal to 6, and it's very close to 1. So the cumulative distribution allows you to evaluate these probabilities. Now we've talked about how to simulate random numbers from simple probability distributions, but the question now is, what if you want to simulate data from a model? So for example, like a linear model. So I've got a very simple linear model here. It has a single predictor x, and it's going to have random noise, what I call epsilon, that has a normal distribution with standard deviation 2. The outcome is going to be generated with using these 2 regression coefficients. I've got an intercept beta naught and a slope beta 1. I'm going to assume that beta naught is equal to 0.5 and beta 1 is equal to 2. So the question is, how do I simulate from this model now that I've specified what it is? So I set the seed. Remember, it's always very important to set that seed. So I set it to 20. I generate x, the predictor, which has a standard normal distribution. I generate epsilon, which is going to have a standard normal distribution with mean 0 and standard deviation 2. And then I'm going to add them all together after multiplying the regression coefficients to generate my y. And so from the summary here, you can see that y has roughly a mean of 0.68. And it ranges from about -6 to +6. And then I can plot the data to see what they look like. And here they are on the next slide. So this is the plot of the x that I simulated and the y that I simulated from the linear model. And you can see that they very clearly have a linear relationship that follows the model that we specified. So just a slight variation of the previous example. What if x is instead of x being a normal random variable, what if x is a binary random variable? So maybe it represents gender, or maybe some treatment versus control or something like that. So here that's very simple. I can generate binary data using the binomial distribution and the R binom function. So I set the seed again. and I generate 100 binomial random variables, and these are going to have this comes from the binomial distribution, which is n equal to 1 and p equal to half. So the probability of 1 is going to be equal to 0.5. So I generate 100 of those. And then I generate my normal random variables, my normal error term, which is going to be mean 0 and standard deviation 2. And then I add them all together to produce my y. So now when I look at the summary of y, I see the mean is about 1.4, and it ranges from about -3 to 6 or 7. So when I plot the data, of course, they'll look very different, because the x variable is binary, but the y variable is still continuous. It's normal. So here you can see that there appears to be a pretty clear, again, linear trend between going from x equal to 0 and x equal to 1. Now suppose we want to simulate from a slightly more complicated model, a generalized linear model, perhaps with a Poisson distribution. And so, for example, we might want to simulate some outcome data that are count variables instead of continuous variables. So we have to use a slightly more complicated approach to do this, in particular because the error distribution is not going to be normal. It's going to be a Poisson distribution. And so let's assume that the outcome y has a Poisson distribution with mean mu, and that the log of mu follows a linear model with the intercept beta naught and a slope beta 1. So x is going to be one of our predictors. So let's assume that beta naught is 0.5 and beta 1 is 0.3. So how do we simulate from this model to get our Poisson data? So we need to use the R-Poise function for this. And so we first set the seed, as always, and we generate our predictor variable x, which is going to have a standard normal distribution. Then we're going to generate our linear predictor log of mu, which is just adding the slope and the intercept and the slope coefficient times x. So that's the log of our linear predictor, but in order to get the mean for our Poisson random variable, we need to exponentiate that. So we simulate 100 of these Poisson random variables using the R-Poise function, and we give it the exponential of our log mean. So when we summarize this, you'll see that the mean is about 1.5, and it ranges between 0 and 6. When I plot this data, you'll see that they look like Poisson data, and that there's clearly a linear relationship between x and y. As x increases, the count for y generally gets larger, but the data are still count variables here. So the last function I want to talk about is the sample function, and the sample function allows you to draw randomly from a specific set of objects that you specify. So if you give it a vector of numbers, it allows you to draw a random sample from that vector of numbers. And so you can kind of create any arbitrary distribution that you want by specifying a vector of objects and then sampling from it. So here, for example, I'm going to sample from the integers 1 to 10. So I pass it the vector of integers 1 through 10, and I tell it that I want to sample randomly 4 of them without replacement. So I'm just choosing 4 random entries from 1 to 10, and here I get 3, 4, 5, 7. If I do it again, I'll get 3, 9, 8, 5. So in this example, I won't get repeated numbers because I'm not sampling with replacement. I don't have to just sample numbers. I could sample letters if I wanted to. So here I'm taking the letters A through Z, and I'm just going to sample 5 of them without replacement, and I just get Q, B, E, X, and P. Now, what happens if I don't specify anything? I just give it the vector of objects. So here I'm passing sample the vector 1 through 10. And if I don't specify anything else, what it does is it gives me a permutation of those. So here the vector 1 through 10 is just permuted in a random order. If I call it again, I get yet another permutation. So lastly, if I want to sample from 1 through 10, but with replacement, I can specify the replace equals true argument. So now I'm sampling 1 through 10. I'm getting a vector of 10 numbers from the vector 1 through 10, but because it's with replacement, I can get repeats. So you can see I got 8 3 times, and I got 9 multiple times. So that's how you sample with replacement. So that's a very quick summary of the simulation functions in R. You can draw random samples from specific probability distributions with the R function, so R norm, R-Poise, R binom we saw already. All the standard distributions are going to be built in that probably you will need. Things like the normal, the Poisson, the binomial, the exponential, gamma, etc. All those functions are built in, and you can use the corresponding R functions to simulate from them. The sample function can be used to draw random samples from arbitrary vectors. So if you want to kind of create your own distribution here, and then it's very important to remember to set the random number generator seed anytime you simulate data in R, so that you can reproduce the results that you got at a later date.